Welcome to Homework Lib.
Here, what we're going to have is the situation in which a student throws a stone from a vertical height of 8 meters at an initial speed of 23.2 meters per second and at an angle theta equal to 22 degrees below the horizontal. So, first of all, the information that we have is that at the origin, we're going to put the initial position of the stone. This is going to be the 0, 0 point, and when it hits the ground, what is going to happen is that the value for y is going to be equal to -8 because the origin was on the top. Now, using a Cartesian coordinate system, we want to know what speed in meters per second does the stone is going to have when it hits the ground. So to do so, the first thing that we're going to do is to notice that the velocity is going to have two components. The initial velocity on x is going to correspond to 23.2 meters per second, my initial velocity, multiplied by the cosine of theta. Why the cosine function? Because if we look at this velocity vector, the x contribution is going to be attached to the adjacent caret, and the y contribution is going to be attached to the opposite caret. So it's going to have a sine of theta. But the y contribution is going to be looking down on our coordinate system. So this needs to be a negative value just to ensure the result. You can use sine of minus 22 degrees, or you can use directly sine of 22 degrees and just add the minus in front of it. Both of the approaches are going to be valid. In this case, we're going to put directly the value of theta equal 22 degrees to get the results for each of them. But so far, we don't need to employ this in order to get our result, right? We want to know the velocity when it hits the ground. So what is going to happen with the velocities on each of the components? The velocity on x as a function of time is going to be equal to my initial velocity plus acceleration on x times time. The same thing is going to happen with the velocity on y as a function of time, and this is going to be initial velocity on y plus acceleration on y times t. Over here, we know that there's going to be no air resistance, so the acceleration on x is going to be 0, and the acceleration on y is going to be equal to minus g. So we can replace directly this value over here, minus g times t. So it seems that we have almost all the information required, but the time that it takes for the rock to hit the ground. So time to hit the ground is going to depend in this case, since the only acceleration that we're going to consider is on the y-axis and the final position is only on the y-axis, is going to be coming from the equations of motion of y. This is going to be initial position plus initial velocity on y times t plus 1/2 acceleration on y times time squared. Over here, my initial position is going to be equal to 0. The initial velocity on y is going to be given by the factor that I already written above, and the acceleration on y, of course, is going to be minus g. So let's replace here. This is going to be a minus, and instead of acceleration on y, minus g. And this needs to be equal to minus 8 meters, because that is going to be the position at the very end over here when we hit the ground. So from here, we can find an equation that tells us that 1/2 of gravity times the squared minus initial velocity on y times time minus 8 is going to be equal to 0. So this is a quadratic expression that we're going to need to solve. So replacing the values with the appropriate ones, we're going to get over here 4.905 times squared. The minus for the initial velocity is going to cancel out with this minus over here. So we're going to end up with plus 23.2 times sine of 22 degrees times t. This value over here is going to be equal to 8.69807 on t minus 8 equal to 0. And guess what? This is nothing but a quadratic expression, so we can directly replace the values and solve as you would do with any quadratic expression. So let's go ahead. This is 8.69807 on t. And you can use either your calculator, software, or the general formula, which tells us that x12, in this case, it would be times 1 and 2, the two possible solutions, would be equal to minus b plus minus square root of b squared minus 4 times ac over 2 times a, where a, b, and c come from an expression that looks like at squared plus bt plus c equals 0, right? So you just need to replace the value on that equation. So these two possible values for time that we get after solving are going to be the first one, a negative value, which is not going to have physical meaning, and the second one, a positive value that does have physical meaning, 66,8063. So the time that it takes for the stone to hit the ground is going to be this value for time. So now we can go back to our equations for velocity. So the velocity on x, as we said, is going to be directly the initial velocity. So this is going to be 22.3 meters per second multiplied by cosine of 22 degrees, which is, oh, sorry, over here, 23.2, not 22.3. 23.2 meters per second, which gives us 21.51 meters per second. Now, as for the velocity on y, we said that the equation had to involve velocity. So this is going to be our initial velocity on y that we already did the calculation over here. 8.69807 meters per second minus 9.81 meters per second squared times the time that it took for the movement to occur, which is 0.66806 seconds. Seconds cancel out with second squared, and the velocity on y, oh, of course, this was a negative value. Let's not make that a small but important mistake. That was negative, as we saw from here. So the velocity on y will be negative 15.2524 meters per second. So the speed when it hits the ground is the absolute value of, well, the norm of the vector, which is going to be bx squared plus by squared. And this is going to be a square root of 21.51 meters per second squared plus minus 15.2524 meters per second squared as well. So the speed at which it hits the ground is going to be rounding up 26.37 meters per second. In this case, all of the velocities were given up to three significant figures, so this would be approximately 26.4 meters per second. And with that, it would be all. Thank you very much and have a good one.